Hi everyone. In this video, we're going to talk about some properties of joint distributions that are going to be important to us sort of later on. And so the first thing that we're going to talk about, although there won't be many examples in this, and it won't require you to do much, these are important topics. So please do pay attention, even though there aren't sort of any your turns and things in these videos. So the first thing that I want to talk about is expected value. And so we know expected value from before, and it's basically the same thing here, okay, except now we just have double sums and double integrals from what we were used to in the last few chapters. And so the expected value is, again, important because it gives you the mean or the center of this joint distribution. And that's often of interest to us because people are often interested in the average or the mean value, and that's where we often make our decisions. When we get to the statistics part of this chapter, we're almost always going to be interested in some type of mean, and so the center is important, and so expected value is important. And so they give you here a general definition of not just the expected value of x and y, but it could be, of course, be a function. And so just as before, to find the expected value of a function of the random variables x and y, you multiply whatever that function is by the probability distribution, and then it's a double sum or a double integral over that. Okay. So that's expected value. Now, something different here is that we can't have a variance of two variables. And so we come to something called, the covariance. So how do two things covary together? Okay. Excuse me. And so there is a formal definition here of what the covariance is. It's the expected value of x minus the mean of x times y minus the mean of y. So there's no real easy way for me to describe why it is the way it is. It's easier it's easier to just believe it and use it. And so in a sense, I'm not going to describe why it is those things, but the expected value, and below they give you how to sort of calculate that. Again, we're going to skip really over that. It's more important you know it's going to give you a number out, and so it's going to be important to be able to interpret that number and sort of understand it. And what covariance is telling you, in a sense, or what it's giving you, is the strength of relationship. And specifically, it's probably a linear relationship, depending on what we're doing, but not always. It's not always going to be a linear-ish relationship. It's a small point that I can't get past because I know the difference, but I'm going to try to just for you because we don't really need to know the difference. But it's a strength of the relationship between x and y. Okay? And so it's going to give you a number out. It could be anything from really negative infinity to infinity. So it could be any real number. And it can be 0 as well. And it tells you, so we want to look at the magnitude of the number, in a sense, and we also want to look at the sign of the number. So it's going to give you one number out, and if the number is positive, then you have a positive relationship between x and y, between the two random variables x and y. So as the value of x goes up, the value of y is also going to go up. If the number is negative, And so that's what we're, the three sort of graphs I have at the bottom of the slide talk about or show this. And so the graph part A there shows a positive relationship. As x increases, y is going to increase as well, or we see that from the relationship and possible outcomes. So as x increases, y is going to increase as well. If the number is negative, that means as x increases, y is going to decrease. And if there's no relationship, so if that's when a covariance will be negative. So when a covariance is negative, there's this sort of inverse relationship between x and y. Okay, so as one goes up, the other one's going to go down. It could be as y goes up, x goes down, or as x goes up, y goes down. Order really doesn't matter here. And if there's no relationship between the two, it doesn't matter as x goes up, y really doesn't do anything, or the other way around, then the covariance will be 0. So 0 means no relationship between x and y. Positive means a positive relationship, and negative means a negative relationship. So that's the sign. The magnitude of the covariance is really hard to distinguish. So generally, you tend to think that because the covariance can be anywhere from negative infinity to infinity, that numbers farther away from 0 are going to make mean a stronger relationship. And numbers that are really negative so numbers farther away from 0 are going to give a stronger relationship. So a really positive number is going to be a really strong relationship, and a really negative number is like a strong negative relationship. But unfortunately, that's not necessarily the case, because the covariance really depends on the units of the problem. And so if my units are large, I'm going to have a huge covariance. And so let's see an example of that. So here's an example of the discrete situation that we've been using so far in the slides, and that's auto and homeowner insurance, and so how they sort of vary together. And so here they did the calculation for the covariance, and the covariance is 136,875. Right? And so that is a very large number. And so what we know from the covariance is that the relationship is positive, which makes sense, as if you have a larger auto insurance policy, you're probably going to have a larger homeowner insurance policy for a number of different reasons. And so we can tell something about the sign of the covariance, but the number being so large, 136,000, only makes sense, or is only there because of the fact that the values of x and y are so large. If those numbers were smaller, and I don't have an example of this, but there are a number in the book, so if you want to look there, if the values of x and y were really small, so if I said 10, 50, and 100, and then 50, 100, and 500, so if I just took zeros off of all the x's and y's values, and I recalculated this, that covariance number is going to go down significantly. And so the magnitude of the number really doesn't tell us much. And that's a flaw in the covariance, because we'd like to see a large number, meaning a stronger relationship, where, depending on it, it doesn't matter what the sign on it is. but we'd like to see larger numbers, stronger relationship. That isn't the case for covariance. So what we need to do is find a new number. And of course, there is a new number, and it's called the correlation. So covariance is an interpretable, at least the magnitude isn't, because it depends on the scale of the random variables, is what I've been saying. We can scale the covariance to be a number that is interpretable. And so scaling means we're just going to divide it here. In a sense, we're dividing it by the standard deviation of both variables, but we're getting it down to the same level. You can think of scaling as the z-scores that we've worked with not too long ago. They were, in a sense, scaling numbers down to a certain normal distribution. So we're doing the same sort of thing here. And so when we do that, when we scale the covariance, we're going to get something called the correlation coefficient. And so you've probably never heard of covariance before, but you probably have heard of correlation. It might not have been in a mathematical sense, but certainly in the world, through what you've gone, what you've seen in popular media, so on and so forth, they've talked about things being correlated. Correlation is a word that's thrown out a lot, often in terms or often paired with causation. And so there's the phrase that correlation does not imply causation. That's a discussion for a different day, but that's the same type of correlation that we're talking about here. And so we get a number, and we're going to call that rho. So that's the Greek symbol rho. It's the correlation coefficient between two random variables, x and y. The properties of the correlation coefficient are as follows. So it can be between -1 and 1 inclusive. So it can include both endpoints. A -1 correlation coefficient means a perfect negative relationship. And so what do we mean by perfect? That means if x increases or decreases, I know exactly how y is going to act. So it's no longer a random thing. In a sense, it means that x and y have some deterministic relationship. So I know if x increases by 1, I know y is going to increase by 2. And so it means that if I plot points on a line of x and y, the relationship, and I plot points on a line, it's going to be on a plane, on the xy plane, it's going to be a perfect line. So -1 is perfect negative. +1 is perfect positive relationship, and then 0 means no relationship at all. Okay, so same sort of thing as the covariance, but now we've just scaled it down to the -1 to 1 scale. And the additional benefit here is that numbers that are we can take the magnitude into account. So a correlation coefficient of -0.9 means a stronger relationship than a correlation coefficient of -0.3. Okay, we couldn't tell that from differences in covariances, but we can with correlation. And so the farther you are away from 0, the stronger the relationship is. Okay, so that's the correlation coefficient, and that ends section 5.2, which was about expectation, covariance, and correlation. Okay, we'll talk about these topics again later on in terms of statistics, more statistical type of things rather than probability type of things. But it's important to sort of mention them and give their formal definition now. And as a last point, the correlation is equal to the covariance divided by the product of the standard deviations of each marginal variable. Okay, so anyway, that's the end of section 5.2, and hopefully you learned something this time. Okay, thanks.